And then David and Laura's team, and I can never pronounce the name correctly.
So we're Team Gambiarra. Yeah, give me 1 second. Let me grab the screen. Okay, can everybody see the slide?
Yes, sir.
Sure can. Calling
Excellent.
out your win early.
All right, so yeah, Team Gambiarra. It's Michael Ellis, Laura Lacerda, and Vinicius, and myself. We decided to do our hackathon around reinforcement learning. And specifically, we chose DeepRacer. So DeepRacer is a reinforcement environment built in AWS. It sits on top of SageMaker and RoboMaker. And it's kind of all batteries included. So you have agents, environments, and algorithms, all kind of the recipes for doing reinforcement learning. What's really cool though is, so it's built on top of RoboMaker, and RoboMaker has the goal of enabling training of real life agents in a virtual environment. So the little virtual cars that you train within DeepRacer, the models can actually be downloaded and put on a 8th scale autonomous race car for running in real life. So it's worth noting the 3 kind of flavors of machine learning and the one that we went with. So there's unsupervised, supervised, and reinforcement. So we didn't give it, unlike with, I think, some of the other projects, which all kind of fall under the supervised umbrella, reinforcement learning, we define a reward, which we'll get into later, which is how we kind of dictate whether the model is doing well or not, rather than defining an output. So we'll get into the technical approach. Laura, do you want to, I can just keep the slide up and you can tell me to click.
Yes,
that works.
Let's do this way. So as we are using the DeepRacer environment to run our reinforcement learning algorithms, first we need to understand what is a reinforcement learning approach. So it's pretty much like we are facing a game-like situation. So we are trying to make the agent, which in this case is the car, to learn by like doing a sequence of actions. So the agent tries to achieve a goal in an uncertain and potentially complex environment. And it tries to employ the trial and error approach. So as the reward increases, in this case, the car maintains in the track, doesn't goes like off the track. The reward increases, and then it's like the agent is doing the right thing. So in the deep car in the deep car environment, we are able to use 2 algorithms, reinforcement learning algorithms. The first one is the proximal policy optimization, which is pretty much like we are using one of the state-of-the-art policy gradient algorithms, and it uses 2 neural networks during the training, a policy network and a value network. Like to define what is a policy network, it's pretty much like it's data hungry, and it tends to be more stable when it's doing the training process. Click. Oh, sorry, and there's like go back, please. Yeah, and there is like the entropy regularization. It pretty much like has less complexity than the next one. So click. So, and there is the second one, the SAC algorithm. So it tends to work better in the continual action space, which means that the agent can do like lots of can choose like between lots of possible actions. It's more off policy, and it add more entropy, so it's a more chaotic algorithm. Click. So for each of them, there's a set of hyperparameters, which is pretty much some parameters that feedback the learning. So they are used to control, especially the learning process. We don't have time to go like over each of them. So for proximity policy optimization algorithms, there's like these hyperparameters. Click. And for the SAC, we have less, but like I said, it's a more complex environment. So we tend to have more actions. The range of actions is bigger than in the previous algorithm. Click. And as we were talking about the action space, it's pretty much we have two types of settings. The first one is a discrete action space, which is we have a finite set of actions that are possible for an agent to take. While in the continuous action space, the agent can choose between a large group of actions. Click.
Sweet. So I had mentioned rewards earlier. So instead of defining an expected output, there's kind of two phases to training these models. There's exploration, and then there's exploitation. And you'll hear a lot of times people talk about convergence in this space, and that's when you kind of start to see your model get these behaviors where they're no longer exploring their environment, they're actually exploiting their environment. And so to reach that, it's all based on a score that it gets. And the score, these rewards can be dictated through a reward function that we write. And that's along with the hyperparameters, that's one of the things that you have a lot of control over when you're setting up training for the agents. So you have everything like, coordinates on the map, the heading angle, waypoints are sort of centered points on the track. Track width is exactly that, how wide your track is, distance from the center, whether your wheels have all left the track or not, speed and steering angle. And so none of those things are inputs that the car is directly aware of. Everything is abstracted through the score to the car. So on the right, you can kind of see this is one that we used in, I believe, our model that we called Fancy. And this model is kind of aware of two things. It's kind of checking progress based on timed steps. So there's sort of a tick. And at each point, we're checking to see how far it is from the previous point or previous step. And we're also checking distance from center. So really the goal here is not so much optimizing things like cornering and some more exploitative behavior, but more just keeping the car on track and trying to optimize speed on straightaways. Some of the obstacles that we saw while working on this, a big piece of reinforcement learning is actually running evaluations on your trained model and then analysis based on that. And we kind of ran into classic issues with using, other people's Docker images and samples code. We ended up hosting our own notebook in SageMaker and then just installed the dependencies that we needed directly in the notebook. And yeah, let me see if I can switch over. I kind of just want to share what we came up with as far as analysis. Sorry, it may stop sharing for 1 second.
So who was on Team Gambiarra?
So it's Michael, Lauro, Vinicius, myself. Oh, and Sean. And I apologize. Sean was on our team as well.
I was not on their team. I was not on their team.
I
was a fly on the wall. That's all I did.
Well, you were good support. You were with us for a good amount on Wednesday, so Okay, so for most of our models, what I tried to do, I didn't get through them all today, was do you can export logs of both your training and evaluation. So training is obviously kind of a report on how it went during training, and evaluation is then you can choose whether you want to run evaluation on the same track that you trained on or a different track, and you can get outputs on how your model behaved there. So this is an output for our model, I believe, Barrichello, which is one that Laura set up. And so the way that I have the output, it's pretty basic. There's a lot that we can kind of get going, but we got the template up yesterday and I started to modify it so that we could get some interesting visuals out of it. First being is that we have a list of completed laps in order of speed. So the quickest lap will be at the top. And then directly below that, we actually have a positional plot of the runs on the tracks. So we can see kind of the behavior and, if there was, some cornering or kind of exploitative behavior. It actually looks like this model is very in favor of cornering. In fact, it looks like it just barely stayed on the track this run. And then the last piece is I pulled a little bit more of a detailed map of our fastest lap. So we take the previous listed data frames and find the one with the shortest runtime. And we can kind of see up close the behavior of one of the better laps that this model ran. So analysis is a big piece of it, because then the idea is you're going to go back and take the same reward and hyperparameters and tweak them and optimize them. So give me 1 second, I'm going to switch back. All right, and I think we'll get into lessons learned, which there's a bunch that we learned from this.
Can I speak about that,
please,
David? Yeah, like we learned like through a lot of models. So the first one was the Gambiarra. What I'm doing, we set like basically the default settings, and we were exploring like both the algorithms and the reward functions that were available, and also the sensors. We learned that we could increase the sensors. So we basically gave a brief description of each like learning that we learned through the models. So we can click, David. So when we have like I think it was 13 models. So we were comparing like the algorithms and the rewarding functions, and you can click. And in the end, we believe that if we can pick one of the models that like have the best performance in terms of staying on track, I would say that was one of the first models that was. Can you go back, David? I think it was, yeah. I think it was, yeah. Overall cornering training clone. That was the one that stayed on track for like all the time, even in the earlier phases of the learning. And we use that model to participate. You can click, David. Let's go to, yeah, to the reInvent open race. So we participated on the reInvent open race. We run our model in there, and we didn't finish at the last position. That was good. That was really good. And yeah, we run our model. So we're gonna show our model running in the virtual environment. I think, David, you can speed up the video. So yeah, it would show that you would gain velocity, you know.
Is it turtle mode?
That's awesome.
Yes. Yeah. So if I could take a minute to speak to some of the learnings. Michael trained some of the initial models, which were named the cornering, and I think this is cornering clone. Yeah. And there were definitely some lessons to be learned from that, with being that there's sort of a trade-off in training time. And it depends on the algorithms too. We noticed PPO is much better if you're expecting to have a shorter training time, probably because it has the regulatory network on top of the training network. But along with limiting how fast you let the car go, we noticed continuous versus discrete actions. Also was picking discrete actions was better if we had a shorter training time. That being that rather than having the full range of, say your steering wheel, where you can kind of put your steering wheel at any position, we say, hey, there's only 2 positions to the left and 2 positions to the right that you can choose. And you can either go 0 miles per hour, a half a mile per hour, or 2 miles per hour, and that's it. So rather than giving it a full spectrum of choices, limiting the choices and the actions that the model can take, obviously then the trade-off is that you have faster training time.
And of course, if we had like more time to run our models, we would, I think we would see more things in the continuous space. So we would run, for instance, the SAC algorithm for like 4 days or 5 days, and we would get like best results from them.
Yes, and to that point, if we have time, it probably only will take a minute. I would love to show everybody how we got started and how easy this is to train your own model. Literally will take me 60 seconds, I think. All right.
Can I ask a question while you're preparing that?
Please.
So what's the difference between on the track or off the track? Is it slower when you're off the track, or is it just a bad thing?
So yeah, there's no rule saying that you're going to go slower. It's literally it's all based on our reward function. So if you could think of the map as a grid, right? And each square on that grid has a score attached to it, right? And so say closer to the center, and this depends on, this would just be one scenario for a reward function, but closer to the center or closer to the waypoints would be very high point squares on that grid. And then the further you get to the edge of your track and eventually off the track, you'd have very low point. And you can even define essentially a stopping grid too, a stopping square on that grid. And that's when you're fully off the track. The easiest way to track that within the function is there's a Boolean return for whether all wheels have left the track or not. So once all wheels have left the track for all our reward functions, that iteration ends and you start a new one.
So this grid that you develop and score the grid yourself, right?
So in our case, there's not actually.
You've been using a metaphor, right? Yeah.
So yeah, the reward function could be as complicated or as simple as you want it to be. It's just a function defined in Python with a set amount of inputs and an expected output, which is really just an integer, or I'm sorry, a float, which is the score. So
that would be adaptive enough to so that you could have it learn to corner better.
You could, and that's sort of where this gets addicting, is figuring out. Corner. Yeah, so you have to figure out how to incentivize your model to do that, because you can't directly instruct it to corner or go faster in straightaways.
I'm with you.
You have to abstract that through the score that you give it based on its behavior.
Right, now so, a complex one, because you want it to accelerate out of the corner, so you want the best cornering line, but you also want that change in velocity at the same time, right?
Exactly. And that's if your goal is to go fast. There's other goals too that exist within the league. One of the other major one being object avoidance. So avoiding boxes that are sitting in the road.
You're thinking like Tesla now. What are you doing?
Yeah. Okay, so I just want to show you guys real quick how to get started with this. So you can come in and actually just search for the DeepRacer resource. So you'll see AWS DeepRacer. And if you're in here the first time, you'll click Create Model. Come down to, I definitely recommend going through the first step. It will kind of go through what we've already iterated in our slideshow, which is what reinforcement learning is and how it applies to DeepRacer. So we give it a name, and then we're going to pick the track that we want it to train on. We'll just train it on the classic Caesars track. It's one of the original tracks. Probably doesn't like the name of it. Yeah, it's too excited. We're going to choose time trial. We'll go with PPO. These are the hyperparameters that we were referring to. So you can see we have different sets of parameters based on the algorithm that we choose. This is the action space that we were talking about. So, continuous action space versus the discrete action space. We'll go with continuous. Lauro has gone ahead and built out a number of vehicles. We'll go with the Gambiarra vehicle. And you can choose sensors, cameras. You can really kind of get into how you want to spec it out. And then here is the reward function where you can actually, based on those 13 parameters, choose how you want to incentivize your agent. And it does give you some examples to get started. So here's one great for time trial. There's a few that are good for time trial, preventing zigzag, staying within the borders, which you can see. I think this is the one that I built mine off of or started with. And then so you choose how long you want it to train for. We won't submit this and then create the model. It will take about 6 minutes. And once it kind of spins up all the resources, you will get a video display so you can see your model actively training in the environment. And it'll also provide you with some visuals as far as like graphs and live output on the training. When it's all done, you can download your logs and then feed it into a notebook like us for analysis and then optimize. Yeah.
So the most important question we're all thinking of, who won?
Hands down, Michael's cars won. So much so that, like I said, 2 of my models last night, I kind of based off learnings from Michael's cars. Really being slow down. I think if you don't,
the secret is to be slow.
Yeah, I think you really need a lot of training time for them to explore going fast.
I was gonna say when they first announced this, that was their biggest tip at reInvent was you don't need to go as fast as you think. And having said that, then watch one of their professional races at last year's reInvent on the live feed. It's incredible how fast they actually go.
Yeah, no, it's amazing. I mean, watching some videos on it, there's people that, they're obviously not training their models in the cloud because they let it run for weeks, if not months, in order to probably achieve those kinds of speeds on a single training session. So that's it. I would say our next steps looking forward would be to then dive into RoboMaker directly and SageMaker directly. Like I said, DeepRacer is really supposed to be an introduction for reinforcement learning. And you can easily then take your models and then go directly into a Jupyter Notebook and SageMaker and continue from there. Does anybody else have any more questions? If not, that's it for us.
Yeah, we're selling our car in Amazon.
Yeah. Yes. Oh, yeah. And another point to that, you can actually buy the DeepRacer car on Amazon if you'd like to load your own models on there and try your models out in real life. That is.
I have a question for Sean in terms of like the marketing takeaway. Like, what was the experience of like doing all this like for you?
It was sort of looking into another world almost because, as we all know, and I will be the first person to say this, I'm not a code tech savvy person at all. And so looking at it from that perspective, actually watching, Lado and David and Michael sort of doing the actual work was really, it's almost like its own language. And marketing is also its own language too. So it's almost like the melding of 2 worlds coming together. So yeah, that was really interesting.
Awesome.